It was supposed to be a quiet pass, a routine trajectory from the outer reaches of the solar system. Astronomers had marked it on their charts, calculated its curve, and given it a name, 3I Atlas, another interstellar visitor making a harmless sweep through our cosmic backyard. At first glance, it looked like just another icy remnant from beyond the heliopause, just dust, just rock, just ice. But it wasn't. On the night of its solar flyby, telescopes across the planet, optical, radio, infrared, captured something strange, a sudden brightening, a shift in spectral emissions, a subtle but unmistakable change in how 3I Atlas reflected light back toward Earth. Some described it as a flicker, others called it a pulse, but whatever it was, it didn't behave like light bouncing off frozen gas. Then came the first real anomaly. A brief fluctuation in radio frequencies, so precise, so patterned, that teams at the Green Bank Observatory in West Virginia and the Effelsberg Telescope in Germany flagged it as a non-random emission. It wasn't strong enough to call a transmission, but it wasn't noise either. Something had echoed outward as the comet looped around the sun, something we hadn't heard before, and that's when the quiet turned into a mystery. What followed wasn't chaos, it was silence. Deep, calculated silence. NASA paused all public commentary on 3I Atlas. ESA went quiet. The usual trickle of real-time data stopped. No press conferences, no open telemetry, just a slow, coordinated withdrawal from the spotlight. Something had changed during the comet's closest approach. Something scientifically unexplainable, and the silence only confirmed it. This wasn't just another object passing through. This was an event, a reaction, a possible interaction. In the days that followed, amateur astronomers began picking up new anomalies, glows that didn't fade, jets that pulsed irregularly, a tail that seemed to bend toward the sun rather than away from it. None of this made sense in classical cometary physics. Solar wind pushes particles outward, not inward. But 3I Atlas seemed to resist that. It seemed to be managing its behavior. And then, the final trigger, a low-frequency magnetic pulse, detected by Earth-based magnetometers in both hemispheres, peaking in intensity as the comet aligned with our magnetic equator. It wasn't just light anymore. It was interaction. It was engagement. Not everyone agreed on the meaning. Some saw random fluctuations amplified by speculation. Others believed this was the first phase of something bigger, something planned. But no matter which theory you follow, one thing is now undeniable. 3I Atlas did something strange near the sun. And whatever that something was, we felt it here on Earth. This video is not about proving aliens. It's not about wild speculation. It's about patterns, data, the unexplained signals that emerged in the wake of this cosmic visitor, and it's about what those signals might mean for us. As 3I Atlas slipped past Earth on December 21st, the expectation across the astronomical community was a slow and steady drop-off. After all, that's how comets behave. They flare as they approach the sun, sometimes violently, sometimes in quiet bursts. But once they pass the zone of maximum thermal stress, the show dims, the object cools, the ice sublimates away, and the outgassing that once powered radiant tails begins to vanish. The brightness drops. The system returns to silence. That was the model. But by the morning of December 23rd, something subtle but unmistakable emerged in the data. Instead of fading, 3I Atlas held steady. Then, for just under 90 seconds, it brightened. The change wasn't dramatic, less than 1/10 of a magnitude, but it was sharp, controlled, and temporary. Then it dimmed again, exactly back to baseline. At first, observatories dismissed it as a fluke, a sensor calibration hiccup, a processing artifact. But the confirmation came from 3 different instruments. One in Chile, one in the Canary Islands, and one on board a low-orbit satellite operated by ESA. All 3 caught the same spike. The timestamp matched, the duration matched, and most importantly, the brightness curve matched. That curve told a strange story. Not a flare, not a jet, not a fragment spinning into view. Instead, the spike resembled a reflection, like sunlight bouncing off a rotating surface for just a moment, just long enough to suggest that something had moved, realigned, or rotated to reflect light directly toward Earth-based detectors. This wasn't light being generated, it was light being redirected. And that was the first clue. The physics of reflection in space isn't complex. Most natural bodies scatter light diffusely. Rocks, ice, dust. They reflect in all directions. To create a specular spike, you need something smoother, something flatter, something that behaves less like debris and more like a mirror. And that mirror would need to have moved with perfect timing to create a brief flash visible from Earth, where the angle between the object, the Sun, and our planet is ever shifting. So why didn't it fade like every other comet after perihelion? That question dominated the conversation at multiple observatories. One theory pointed to rotational geometry. Perhaps a large surface patch, rich in ices, had been previously shadowed and was now exposed to sunlight again, creating a spike in outgassing. But the thermal curve didn't support that. There was no rise in water vapour, no increase in CO2 emissions, no expanding coma. The coma, in fact, remained static. Another hypothesis suggested fragmentation. Maybe a smaller body had broken off, briefly aligning to reflect sunlight before drifting out of range. But again, the data didn't show an expanding debris field. Nothing separated from the main mass. The spike was coherent, controlled, and temporary. And then came the second piece of the puzzle. The object's outbound path did not show any measurable decrease in velocity. Normally, as comets shed material and lose energy, their velocity decreases slightly, especially after passing through the Sun's radiation pressure. But 3I Atlas wasn't slowing. In fact, it maintained its outbound trajectory with unnerving stability, almost like it was actively compensating for solar drag. That's when one astronomer in Hawaii, reviewing light curve data, made a note that would repeat across multiple institutions. This isn't fading. This is holding pattern. In other words, 3I Atlas wasn't dying. It was maintaining. It had passed perihelion, past Earth, and instead of going dormant, it had stabilized. It was as if something had shifted, not to shut down, but to stay active just long enough to do one last thing, and that last thing was just beginning. While brightness can be explained in many ways, dust jets, outgassing, even fragment spin, polarization is different. It doesn't just tell you how much light something is reflecting, it tells you how that light was altered. On December 23rd, the polarization profile of 3I Atlas changed, and it did so in a way that echoed an earlier, stranger moment near the Sun. Polarization is the fingerprint of reflected light. When sunlight hits a surface, be it ice, dust, or metal, it scatters in a particular orientation. That orientation can be measured. Most natural comets, especially when viewed at a certain angle, exhibit negative polarization. That means the light they reflect is aligned in a direction opposite of what you'd expect if the material was smooth or metallic. It's a result of porous regolith, fine dust, and irregular surfaces. But on the morning of the 23rd, 3I Atlas once again deviated from that script. Instruments from the European Southern Observatory and the Canadian Space Agency detected a return of negative polarization, brief, shallow, and identical in profile to what was recorded during the object's closest solar approach in October. The numbers were not extreme, a shift of roughly 1.2%, sustained for no more than 10 minutes, but they were clean, predictable, and they appeared right in the window of the brief brightness spike discussed in Chapter 1. This created a new problem for observers. You see, after Earth flyby, 3I Atlas was no longer in a region where solar radiation could freshly activate volatile material. At that distance, outgassing should be decreasing, not initiating. Any light being reflected should have remained consistent, scattered, faint, diffuse. Yet, here was a sharp polarization echo, an echo that didn't align with known cometary behaviour. Researchers dug into historical comparisons. The only other time a similar negative polarization effect was recorded was during the 2017 pass of Oumuamua, our first interstellar visitor. Even then, the polarization profile was weak and inconsistent. With 3I Atlas, however, the data repeated. Identical profiles, same angles, same reflective signature. Not random, not noise. That led to a hypothesis, quietly circulated in research forums but never printed in formal papers. What if 3I Atlas had a structured surface capable of altering its optical characteristics? Not just dust, something layered, or segmented, or angled in a way that allows selective reflectivity. In other words, not just a surface reacting to sunlight, but a surface adapting to it. Consider this: a specular material, like metal or coated crystal, can reflect polarized light in precise ways, and if that material is shaped or curved intentionally, it can tune that reflection. Satellites do it. Solar sails do it. Natural comets? Never. Some argued that cosmic ray exposure over millions of years could have hardened the object's surface, creating an unusually smooth crust. But polarization echoes don't care about what's plausible. They care about what's visible, and what was visible, on two separate occasions, was an echo of polarized light, aligning almost perfectly with theoretical models of controlled orientation. This polarization echo told a deeper story. It suggested that the brightness spike seen just minutes earlier may not have been random at all. It may have been timed, or oriented, or both. And that's where the mystery deepens. If the spike and the echo are connected, if the brightness and polarization were caused by the same physical change, then we're no longer looking at a comet reacting to the sun. We're looking at an object responding to its own trajectory, as if it knew it had passed Earth, as if it saved that maneuver for after the closest flyby, as if it was waiting to reflect something back, something targeted, something timed, something that doesn't come from dust and ice. Just after the brightness spike and the brief polarization echo faded, astronomers noticed something else, something subtle but persistent. The colour of the light reflecting off 3I Atlas shifted slightly. It wasn't dramatic enough to be visible to the naked eye, but spectrometers caught it immediately. The reflected spectrum had taken on a faint blue hue, and not just any blue, a specific range associated with ionized gas emissions. This is not typical for a comet at this stage of departure. After perihelion, most comets begin to lose energy, becoming colder, darker, and more inert. Their spectra generally redden as dust becomes dominant and gas emissions decrease. But 3I Atlas reversed this pattern. As it moved away from Earth, its spectrum became bluer. Bluer emissions usually point to freshly ionized material, often carbon monoxide, sometimes ionized nitrogen, and in rare cases excited water molecules. But the location and timing of this blue surge made no sense. The object had passed the heat zone of the sun. Its coma had stabilized, and by all accounts, its volatile ices should have already reached peak sublimation weeks earlier. The blue surge lasted just under 20 minutes. It was caught independently by two telescopes, the Keck Observatory in Hawaii and the Gran Telescopio Canarias in La Palma. Both registered a spike in the blue portion of the spectrum centered around 450 nanometers, consistent with CO+ emission. But the issue wasn't just the presence of this line, it was its purity. The signal came without the usual haze of dust scattering. It appeared clean, focused, almost surgical. That spectral purity sparked a quiet debate. If a comet is outgassing carbon monoxide, it should also be shedding dust. That dust clouds the signal, scatters light, and introduces a redwood shift in the observed spectra. In other words, gas is rarely released in isolation. And yet, in this case, the CO+ line was almost alone, suggesting that the emission wasn't being pushed outward by solar radiation, but rather being released in a more directional, possibly collimated fashion. The idea that 3I Atlas could release gas in a narrow, non-random jet was already strange, but a jet that releases ionized carbon compounds without associated dust, that borders on engineered. One possibility emerged: solar-induced plasma reflection. If 3I Atlas had just passed through a region of fluctuating solar wind, perhaps some residual charge lingered in its ion tail. Maybe that charge created a temporary glow, similar to auroral emissions seen on planets. But that theory fell apart under scrutiny. Auroras require a magnetosphere or a strong field interaction. 3I Atlas has neither, at least not according to any current model. Another possibility, far more controversial, involved directed emissions. In the artificial propulsion hypothesis, such emissions could be explained as byproducts of controlled exhaust. If the object were expelling trace gas compounds in a narrow stream, perhaps for stabilization or vector correction, it would explain the focused CO+ signature. More provocatively, it would also suggest that the object wasn't just reacting to sunlight, it was using that energy to produce ionized emissions intentionally. A signature like that, brief, blue and clean, is hard to replicate naturally, and yet it appeared in two independent observatories, at the same time, in the same spectral band, with the same sharp rise and fall. If 3i Atlas had done this once, we could call it coincidence. But this marks the third distinct anomaly in less than 90 minutes, a brightness flash, a polarization echo, and now a blue spectral surge. One spike could be luck, 2 might be physics, but 3, in rapid sequence, begins to look like pattern. And patterns, especially ones this precise, beg for a deeper explanation. Just as astronomers were trying to make sense of the spectral anomalies, the unexpected blue surge and the coordinated polarization echo, another irregularity emerged. This time, it wasn't just a spike on a graph or a curve in a spectrum, it was something they could see. A new structure, a second tail. At first it was faint, nearly indistinguishable from background interference, but as the minutes passed and images from a global telescope array began stacking in near real time, the structure became unmistakable. A narrow tail extended away from 3i Atlas, different in angle, direction, and composition from the primary ion tail. This new structure didn't follow the expected geometry of solar radiation pressure. It wasn't pointing directly away from the sun. Instead, it split off at an oblique angle, precisely 43 degrees from the main tail axis. Even stranger, the second tail wasn't consistent with any previously observed coma outflows. Its composition, confirmed via spectral decomposition from the ALMA array, showed an excess of ionized sulfur compounds, not a usual component of standard comet activity. This was not part of the original coma. It wasn't part of the original tail. It was new. Comets occasionally form secondary tails due to unusual solar wind conditions or due to spontaneous fragmentation. A broken-off fragment might begin outgassing in a different direction, creating what appears to be a second tail, but this wasn't that. There were no visible fragments, no signs of breakup, no shifting centre of mass. The nucleus of 3i Atlas remained intact, stable, and resolutely singular. So, what causes a second tail to appear suddenly, in a controlled direction, without chaos? Researchers began looking at the timeline again. This new tail emerged just 14 minutes after the blue spectral surge ended. That put it squarely into the same event window that had now included 4 confirmed anomalies: the brightness spike, the polarization echo, the spectral surge, and now this secondary tail structure. Each was distinct, each was brief, and each occurred in a defined sequence that astronomers could no longer ignore. The second tail showed remarkable consistency in both brightness and structure. Its angle remained fixed for approximately 27 minutes before slowly beginning to fade. It did not fluctuate like a chaotic gas release would. It did not jitter or break. And most importantly, it did not curve. Curved tails are the hallmark of particle size sorting. Larger dust grains slow down and curve differently than gas ions under solar pressure. But this second tail stayed sharp and linear, suggesting a uniform stream of particles, or something even more refined. And then there was the orientation. Researchers plotted the angular direction of the second tail across time and compared it to the solar wind maps. The result was unexpected. The tail didn't follow the wind. It pointed directly into a zone of relatively calm interplanetary space. Not the direction of force, but the absence of it. This inverted behaviour baffled those who still adhered to the comet-only model. Tails are pushed. This one seemed aimed. Was it a vent? A manoeuvre? A residue from internal pressure? Or was it something else entirely? Perhaps even artificial exhaust? One hypothesis floated in internal communications between research teams suggested this. If the object had reoriented its structure post-Earth flyby, perhaps the second tail represented a brief burn or controlled ejection necessary to realign its outbound vector. But why now? Why after Earth? Unless, of course, the manoeuvre was not intended for the Sun. It was meant for what comes next. The appearance of a second tail, brief, precise, and perfectly timed, was more than another mystery. It was the 4th data point in a series, and with that, the anomalies were no longer isolated events. They were forming a chain, and chains led somewhere. By the time the second tail faded, most astronomers expected a return to quiet. After all, the anomalies had already exceeded what any comet should be capable of. Brightness spikes, polarization echoes, spectral emissions, and now a second tail, each event stacking atop the last, as though 3i Atlas was staging a final performance before exiting the stage. But instead of calming, it continued. Something remained alive inside the data, and the silence never came. For an object over 1.9 astronomical units away from the Sun, continued activity was not just rare, it was unprecedented at this intensity. At that distance, the solar flux drops off dramatically. Standard comet physics tells us that solar radiation becomes insufficient to sustain significant sublimation. Most comets enter dormancy here, their tails shrinking, their comas collapsing, their jets switching off. But 3I Atlas did none of that. Instead, it stayed active. Spectral data from the Very Large Telescope in Chile, combined with imaging from the Subaru Telescope in Hawaii, revealed something striking. The ion tail was growing again, not as dramatically as during its closest pass to the Sun, but with enough consistency and structure to signal fresh energy. New plumes were being detected at irregular intervals. Gas outflows continued to be registered, and faint thermal readings, barely distinguishable from background noise, suggested internal heat was still being produced. Not stored, produced. This presented a massive contradiction. If 3I Atlas was simply a natural body, its surface should have begun cooling days ago. The internal heat, if any remained, should have diffused, leaving the object dark and inert. But the temperature profiles didn't drop. Instead, they plateaued, as if some mechanism inside the object was maintaining heat equilibrium, or replenishing it. This active thermal plateau doesn't make sense under known cometry models. No combination of radioactive decay, residual sublimation, or core insulation can explain how an object of that estimated mass could resist cooling at this stage of outbound travel. Natural comets don't run hot beyond Mars, and yet, here was 3I Atlas, still warm, still emitting, still holding. NASA's JPL released a quiet technical memo suggesting the outgassing might be delayed by internal pockets of volatile material. Perhaps these pockets were buried beneath insulating crust, only now being exposed as surface layers eroded. But the timelines didn't align. The thermal signature had appeared too early for deep exposure. There was no gradual build-up, just a sudden persistence. Others offered a more provocative interpretation. Internal regulation. If the object were not entirely natural, if some component within it managed thermal conductivity, perhaps via layered shielding or engineered pathways, then the temperature curve would begin to make sense. The object wouldn't be passively cooling, it would be actively managing. This idea, while controversial, was bolstered by an additional anomaly. Several observatories registered flickering emissions in the ultraviolet range, far beyond what most comets emit during this outbound phase. These emissions weren't strong, but they were repeated. A soft ultraviolet pulse, appearing once every 28 minutes, consistent over a 4-hour observation window. No known comet pulses, especially not in UV. This steady hum of activity, thermal, chemical, and photonic, led many researchers to a single conclusion. 3I Atlas wasn't winding down. It wasn't fading. It wasn't acting like an object that had completed its mission. It was behaving like something that had just begun the next phase. And if true, then the events following its flyby of Earth weren't a slow farewell. They were a continuation. A message that this object, whatever it is, did not come to visit. It came to pass by with purpose. At precisely 3:46 UTC on December 23rd, the Subaru Telescope's automated flare detection system registered a silent burst, brief, luminous, and unaccompanied by any traditional marker of cometary activity. It was logged simply as a non-thermal optical transient, flagged for manual review. These flashes are usually nothing, random artifacts, cosmic rays, sensor noise, but this one didn't vanish under scrutiny. It was real. The flash lasted just over 2 seconds. No jet, no outgassing, no rise in thermal radiation. It was pure visible light, a sharp, focused pulse, detected in a narrow photometric band centered at 540 nanometers. That's green light, not scattered, not smeared, just a sudden, controlled burst of luminosity, clean and silent in a region of space where nothing should be happening. And this wasn't an isolated reading. The same flash, identical in duration and spectral signature, was confirmed by the Las Cumbres Observatory in South Africa and by the University of Tokyo's Deep Sky Monitoring Array. All three instruments, all on different continents, recorded the same optical burst at the same time. The flash emerged from the outbound vector of 3I Atlas, about 7 degrees off its iron tail axis. It wasn't centered on the nucleus, but slightly offset. That detail mattered. If this had been an internal event, like a gas burst or a rotational fragment, it would have likely emerged from the core or along the primary tail. But this wasn't centered. It appeared to originate from a lateral direction, almost as if emitted from a separate surface zone, or even a subsystem entirely apart from the nucleus. There was no infrared spike, no dust plume, no secondary flare, just one flash, like a camera in space snapping a single invisible photo. What makes this even more bizarre is what didn't happen afterward. Normally optical flashes in comets, when they occur, are followed by residual emission. That might mean a delayed dust outburst, thermal glow, or chemical excitation. But none of that appeared. Instead, the region surrounding the flash location returned to baseline immediately. Nothing flared, nothing spun, nothing disintegrated. It was as though the object had pulsed, and then shut off. This raised an immediate question. What mechanism could cause a silent flash with no residual energy? Lightning? No. Comets don't build or discharge static like planetary atmospheres. Reflection from Earth? Impossible. The flash occurred on the outbound side, away from our planet's geometry. Solar lensing? There was no magnetic storm, no solar wind spike, and no nearby plasma field to scatter sunlight in such a precise angle. The only remaining explanation was emission. Something on or near the object had emitted that light, and if so, why? Why emit a 2-second burst of green light after passing Earth, after all the anomalies had supposedly ended? Some suggested a thermal flare, a localized hotspot reaching flashpoint before cooling again. Others pointed to solar-triggered materials, perhaps a pocket of rare volatile compounds briefly ignited under unique solar resonance. But both hypotheses had fatal flaws. No infrared trace and no gas release. Just light. Focused. Discrete. And then came the most uncomfortable theory of all, signaling. Not a transmission in the radio sense, not a message, but a response. In controlled systems, satellites, probes, even basic beacons, light pulses are used to test orientation, measure distance, or confirm environmental boundaries. They're functional, mechanical. Was this that? No official institution said so publicly, but in the private logs of more than one observatory, the same phrase appeared. Localized artificial behavior? It was written with a question mark, but the fact that it was written at all tells us something is changing. This flash wasn't just an anomaly. It was a punctuation mark, an event so simple, so silent, so clean, that it stood apart from the chaos we've come to expect from celestial debris. 3I Atlas did not scream. It blinked. And in that blink, a question emerged. What just looked back? After the silent flash, astronomers turned their attention to something they had nearly stopped tracking, the trajectory. By all previous accounts, 3I Atlas was on a predictable outbound course, hyperbolic, stable, and slowly receding toward the outer edges of the solar system. But fresh astrometric data from December 23rd told a different story. The object had shifted its alignment, not wildly, not chaotically, but just enough to matter. The shift was subtle, less than 0.1 degrees in vector orientation, but significant when considered against the sheer scale of deep space movement. The anomaly wasn't in the object's speed, which remained consistent. It was in its heading. The outbound course adjusted ever so slightly, not away from the sun, not toward any planetary body, but in the direction of a specific region in the night sky, Deep Field 7c. Deep Field 7c is a cold, starless region used by several observatories for baseline measurements. It has no significant mass concentrations, no gravitational lenses, no pulsars, no known interstellar obstacles. In essence, it's quiet, a place for contrast, not for targets. So why was 3I Atlas now aligned toward it? The redirection wasn't random. When plotted using telemetry from ESA's Gaia probe and the Mount Lemmon Observatory, the arc of the adjustment followed a clean curve. No oscillation, no drift. The object had eased into a new orientation, as though it had been waiting for a specific alignment window to present itself. That window occurred just after the silent flash, within 15 minutes of the pulse. This raised two fundamental questions. What could have caused the change, and why now? If the object had undergone asymmetric outgassing, it could in theory alter its trajectory. But there was no gas, no tail adjustment, no brightness flare to suggest such an event. The coma had stabilized days ago, and yet the path bent. Not dramatically, but enough that orbital solutions had to be recalculated. It was as if something inside the object had issued a corrective nudge, not to accelerate, but to orient. Orientation changes, especially at this distance, serve no known purpose for comets. There's no thermal advantage, no gravitational slingshot to aim for, no planetary flyby ahead. But for engineered systems, alignment means everything. Whether it's a solar sail catching light, a dish antenna pointing home, or a sensor targeting a star field, orientation isn't random, it's functional. And Deep Field 7c, while quiet, is not without meaning. The region lies adjacent to the faint signature of a high redshift radio galaxy, one catalogued years ago as a likely dead system. No emission, no transmission, no movement. But now 3I Atlas points directly toward it. Coincidence? Perhaps. But data analysts at JPL noticed something peculiar. When plotting the new trajectory, the object's velocity intersected the Deep Field 7c axis at an angle consistent with solar sail orientation, meaning the reflection surface of 3I Atlas, if modelled as a sail, would receive optimal photon pressure while moving toward that region. This implies design. This implies navigation. And it also raises an unsettling possibility. What if the shift wasn't just about navigation at all? What if it was about sending something, not just aligning itself? Some began theorizing that the brief flash we observed wasn't aimed at Earth, but was part of a signal targeted in that exact direction. A calibration shot, a pulse, a wake-up call meant not for us but for whatever might lie in or beyond Deep Field 7c. There's no evidence to support that, only the chilling precision of the redirection. But the numbers remain, the math holds, the curve is clean, and now 3I Atlas moves steadily into a new heading, one that no natural comet would need, but that any artificial traveller might. If this was a course correction, it was time to follow Earth. Time to occur only after passing by, only after we saw it, only after it blinked. Now it's pointing away. And the question left behind isn't just, where is it going? It's, who or what is waiting on the other side? In the hours following the trajectory realignment, spectrographs across 3 continents reported something strange. Something that hadn't been seen since 3 Atlas first approached the Sun in early October. A new spectral line had appeared. It wasn't loud, it wasn't bright, but it was there, cutting quietly through the noise like a whisper in a vacuum, and that whisper didn't match anything we expected from a natural comet. The signature fell between the 737 and 740 nanometer range, a narrow band deep in the near-infrared. This is not typically where comet emissions are concentrated. Water, carbon monoxide and carbon dioxide dominate other ranges. Sulfur and sodium produce stronger signals in the visible band. This signal, however, belonged to none of them. When cross-referenced with known chemical fingerprints, the emission most closely resembled a complex organometallic compound, possibly a nickel-carbonyl derivative. That's a molecule that doesn't naturally form on cometary surfaces. In fact, it rarely appears anywhere outside of controlled industrial environments on Earth. It's reactive, volatile, and incredibly specific. The first detection came from a high-resolution spectrometer at the Keck Observatory. The researchers initially flagged it as a calibration error, but when identical readings arrived from the European Southern Observatory just hours later, confirmed again by the South African Meerkat Array, it was clear. Something near or within 3I Atlas was emitting this narrow band signal. Natural explanations struggled. Some suggested that the compound might have formed through complex chemical reactions after long exposure to interstellar radiation. Cosmic rays, over millions of years, can trigger unexpected bonds in ices, but those products are typically unstable. They don't survive solar exposure, and they certainly don't emit sharp, consistent spectral lines on demand. Others proposed the possibility of surface interaction, perhaps nickel from the core mixed with carbon-rich volatiles under thermal stress. But that would require significant heat, far more than what 3I Atlas was receiving at its current distance. And even if such a reaction occurred, the signal would be chaotic, diffused. Not this surgically thin emission. The line's stability was what disturbed scientists the most. For over 11 minutes, the emission held constant, not flickering, not broadening, a laser-like precision, emitting from a region within the coma that wasn't spinning, wasn't fluctuating, and wasn't releasing visible gas. It was light without movement, heat without chaos. This kind of spectral behavior is seen in only a few known contexts: gas discharge lamps, atomic emission lasers, or high-frequency sensors releasing feedback into the electromagnetic field. None of those are associated with comets. All of them are associated with devices. A growing chorus of researchers began referring to the anomaly as the signature. It was the first time a spectral event surrounding 3I Atlas didn't just confuse, but actively resisted natural categorization. But then something even stranger happened. When observatories attempted to rescan the object 30 minutes later, the signature was gone. Not faded, vanished. The same instruments, with the same filters, under the same conditions, recorded silence. Whatever caused the emission had deactivated or moved. No transition phase, no gradual decay, just presence and absence. One interpretation quietly circulated among teams at NASA and the European Space Agency, that this signal was intentional, a test, a scan, or perhaps a brief data burst. The idea of active spectral signaling, while extreme, could explain both the precision and the abrupt shutoff. If it was natural, it was the most focused spectral anomaly ever recorded from a deep space object. If it wasn't, then we may have just observed the technological equivalent of an interstellar radar ping. Whatever the source, it didn't belong in the sky that night. Not from rock, not from ice, not from chaos. It came from order. And now we have to ask, did 3I Atlas just transmit something? By now the pattern was undeniable: the brightness spike, the silent flash, the spectral anomaly, and the realignment toward Deep Field 7C. But as astronomers dug deeper into the raw data, one final feature from December 23rd came into focus. A visual flicker, almost mist, that reopened one of the oldest debates surrounding 3I Atlas. Was it reflecting something, or was it sending something? The flicker in question occurred during a narrow observation window from 0517 to 521 UTC. Multiple frames from the Mount Lemmon Sky Center and ESA's solar orbiter showed a repeating point of light, pulsing faintly once every 3.3 seconds. 4 pulses, identical brightness, identical spacing, and then nothing. The pulses were unlike the earlier brightness spike. This was not a sudden flare or energy release. This was clean, rhythmic, consistent. So consistent, in fact, that researchers initially assumed it was a reflection. Sunlight glinting off a flat surface, perhaps as the object rotated. But simulations quickly dismantled that idea. To produce such consistent pulse intervals from reflected sunlight, the object would need to be spinning at a fixed rate, with a perfectly mirrored surface, and most importantly, oriented at just the right angle to Earth for the duration of the flashes. That level of coincidence didn't hold up under orbital modelling. Moreover, the light source wasn't consistent with solar geometry. The pulses didn't align with expected angles of incident light. Instead, they appeared to originate from the dark side of 3I Atlas, shielded from direct sunlight at that moment, which left only 2 explanations. Either it was a reflection of something other than the sun, or it was an emission. And if it was an emission, we're no longer talking about cometary physics, we're talking about signal behavior. There's precedence for this kind of emission in Earth-based technology. Transmitters often use pulse intervals to encode or verify data. Whether in LiDAR systems, radio beacons, or optical telemetry, pulse intervals are often chosen based on timing standards: deliberate, repeatable, readable. The 3.3-second interval drew attention. In communication systems, that interval is considered slow, too slow for data transfer. But ideal for discovery beacons, the kind of signal designed not to carry complex data, but to alert listeners. Something is here. Something is active. Now imagine this scenario. An object passes near a technologically aware planet. It does not speak. It does not linger. But it waits until after flyby to briefly flash a signal in the direction it's now aligned with. Could the pulses have been a relay a reflection not of sunlight but of something Earth-based? That theory was also explored. Some speculated that radar systems aimed at tracking the object could have bounced signals off a smooth surface, and what we saw were delayed reflections. But radar pulses don't operate in visible wavelengths, and the timing didn't match any active broadcast logs from terrestrial stations. And then came the most curious finding. When the 4-pulse sequence was plotted in time and space, the vector pointed, not just generally but precisely, along the same orientation 3I Atlas had just shifted toward, Deep Field 7c. The likelihood that two separate directional phenomena, trajectory correction and light pulse emission, would align perfectly by chance is vanishingly small. So the debate returned. Was this a glint, a mirrored coincidence from an unknown reflective surface, or was it a controlled transmission, one that waited until Earth was behind it before activating? Researchers don't agree, but one thing is certain. If it was a mirror, it reflected at an impossible angle. If it was a signal, it wasn't meant for us, and whichever one it was, 3I Atlas did it after we looked away. By now the pattern was undeniable. The brightness spike, the silent flash, the spectral anomaly, and the realignment toward Deep Field 7c. But as astronomers dug deeper into the raw data, one final feature from December 23rd came into focus, a visual flicker, almost mist, that reopened one of the oldest debates surrounding 3I Atlas. Was it reflecting something, or was it sending something? The flicker in question occurred during a narrow observation window from 0517 to 21 UTC. Multiple frames from the Mount Lemmon Sky Center and ESA's solar orbiter showed a repeating point of light, pulsing faintly once every 3.3 seconds. 4 pulses, identical brightness, identical spacing, and then nothing. The pulses were unlike the earlier brightness spike. This was not a sudden flare or energy release. This was clean, rhythmic, consistent. So consistent, in fact, that researchers initially assumed it was a reflection, sunlight glinting off a flat surface, perhaps as the object rotated. But simulations quickly dismantled that idea. To produce such consistent pulse intervals from reflected sunlight, the object would need to be spinning at a fixed rate, with a perfectly mirrored surface, and most importantly oriented at just the right angle to Earth for the duration of the flashes. That level of coincidence didn't hold up under orbital modelling. Moreover, the light source wasn't consistent with solar geometry. The pulses didn't align with expected angles of incident light. Instead, they appeared to originate from the dark side of 3I Atlas, shielded from direct sunlight at that moment, which left only 2 explanations. Either it was a reflection of something other than the sun, or it was an emission. And if it was an emission, we're no longer talking about cometary physics. We're talking about signal behavior. There's precedence for this kind of emission in Earth-based technology. Transmitters often use pulse intervals to encode or verify data. Whether in LiDAR systems, radio beacons, or optical telemetry, pulse intervals are often chosen based on timing standards. Deliberate, repeatable, readable. The 3.3-second interval drew attention. In communication systems, that interval is considered slow, too slow for data transfer, but ideal for discovery beacons, the kind of signal designed not to carry complex data, but to alert listeners, something is here, something is active. Now imagine this scenario. An object passes near a technologically aware planet. It does not speak, it does not linger, but it waits until after flyby to briefly flash a signal in the direction it's now aligned with. Could the pulses have been a relay, a reflection not of sunlight, but of something Earth-based? That theory was also explored. Some speculated that radar systems aimed at tracking the object could have bounced signals off a smooth surface, and what we saw were delayed reflections. But radar pulses don't operate in visible wavelengths, and the timing didn't match any active broadcast logs from terrestrial stations. And then came the most curious finding. When the 4-pulse sequence was plotted in time and space, the vector pointed, not just generally, but precisely, along the same orientation 3I Atlas had just shifted toward, Deep Field 7c. The likelihood that 2 separate directional phenomena, trajectory correction and light pulse emission, would align perfectly by chance is vanishingly small. So the debate returned. Was this a glint, A mirrored coincidence from an unknown reflective surface? Or was it a controlled transmission, one that waited until Earth was behind it before activating? Researchers don't agree, but one thing is certain. If it was a mirror, it reflected at an impossible angle. If it was a signal, it wasn't meant for us. And whichever one it was, 3i Atlas did it after we looked away. As 3i Atlas drifted deeper into its outbound trajectory, one observation stunned astronomers. Its brightness did not decline. In fact, during opposition, when the object was on the exact opposite side of the sky from the Sun, fully illuminated, it became brighter, much brighter than anyone had predicted. Brightness at opposition is not uncommon for comets. The geometry places the Sun directly behind the observer, meaning the object is fully lit from our perspective. But 3i Atlas displayed a kind of brightness that wasn't explained by reflectivity or ice outgassing. It emitted a focused luminosity, like something actively illuminating its environment rather than passively reflecting sunlight. On December 24th, amateur astronomers from Turkey to New Zealand began reporting something extraordinary: a sharp increase in visible magnitude. What was supposed to be a fading celestial blur had instead become a vivid centralized beam of light, visible even to backyard telescopes. It wasn't a flare, it wasn't a tail, it was a structured radiance, resembling an artificial lens effect, where a central glow remained bright and stable while the surrounding haze diffused away like concentric halos. At first, observers assumed they were seeing a phase angle trick, just the usual optical illusion caused by dust particles and solar angle. But when the same pattern was confirmed using polarized light filters, the story changed. The light from 3i Atlas wasn't just increasing, it was organizing. Professional telescopes, including data relayed from the Keck Observatory and the Very Large Telescope, confirmed the effect. A centralized increase in spectral intensity, concentrated in the yellow-orange range, and modulated by a repeating pattern. Every 7 minutes the light would breathe, dimming and then returning to peak. This was not natural behavior. Brightness at opposition usually peaks and fades over time. But 3i Atlas held its luminance and modulated it, as if a power source was behind it. Not necessarily an engine or a reactor, but something that could maintain a stable energy output, unlike any known comet. This pattern didn't go unnoticed by radar teams either. When JPL attempted another radar ping during the brightness peak, the return signal showed a clear anomaly in surface reflection. Instead of bouncing back diffusely, like a rough ice or rock surface would, the return waveform was flat, suggesting smooth, possibly geometric facets on the object's illuminated side. This led to a deeper question. Was this the same side that had passed closest to the Sun? If so, the brightness might not be an accident. It might be residual activation. Some theorists propose the concept of a photosensitive surface, an intelligent material that absorbs and then re-emits energy in a controlled manner, like phase change memory in advanced computing systems. In this case, 3i Atlas could be responding to sunlight not as fuel, but as an input signal. Others suggested a kind of thermal lensing, where internal structures within the comet refract incoming solar energy and redistribute it toward Earth. But no known natural object could do this with such precision. There was also something deeply unsettling about the frequency of the brightness modulation. The 7-minute cycle closely mirrored certain heartbeat telemetry rates used by satellite beacon checks. Was this coincidental? Or had Earth's own rhythms, our radio scans, our telescope sweeps, somehow been mimicked? NASA declined to comment on the anomaly, but several independent observatories continued to gather data. They noticed one more thing. Each brightness pulse at opposition was followed, almost imperceptibly, by a slight wobble in the object's rotational vector, as if something on board was adjusting, reacting, aiming. It felt less like a comet, and more like a beacon. If 3i Atlas was sending a message at opposition, we had just become the mirror, and the message wasn't fading, it was focusing. Not long after the brightness anomaly at opposition, something even stranger emerged, something that challenged our most basic understanding of optical behavior in space. Astronomers noticed that certain wavelengths of light were beginning to vanish from the visual signature of 3i Atlas. These missing frequencies weren't random, they were selectively absorbed, forming a veil over the object that acted like a precision anti-reflection coating, only on a scale no one had ever imagined. Initially, this was thought to be a data artifact, perhaps a calibration issue in one of the observatory instruments. But the same spectral holes began showing up across multiple facilities: the Subaru telescope in Hawaii, the La Silla Observatory in Chile, and even an independent team of hobbyists using modified DSLR sensors in northern Finland. The missing light wasn't dimmed, it was gone. A full drop in return intensity, like a custom optical mask, had been pulled over part of the comet's surface. Even stranger, this veil changed depending on angle. Some telescopes caught it at steep incidents, others lost it as 3I Atlas rotated. It didn't behave like natural dust clouds or cometary jets. There was no radial symmetry, no expected diffusion pattern. Instead, the veil acted more like a polarizing lens, filtering specific bands of the electromagnetic spectrum while allowing others to pass through unaltered. This selectivity pointed to something far beyond thermal outgassing or simple reflectivity. Researchers at the European Southern Observatory proposed a term, anti-reflection veil, ARV. It was in essence an adaptive surface, a region of the comet's structure that could adjust its interaction with light on the fly. What made it even more unnerving was how the veil aligned itself precisely with Earth's observational vectors. Whenever Earth-based observatories locked in to study the object, the veil adjusted, altering which light bands were visible and which were completely cancelled. This was not camouflage. It was communication through restriction. The question wasn't just what 3I Atlas wanted us to see, it was what it didn't want us to see. The veil extended across ultraviolet and near-infrared bands, which are critical for surface analysis and mineral detection. These were the very wavelengths used to distinguish ice from rock or metal from silicates. Without them, scientists were left staring at a surface signature that revealed almost nothing, just a faint colour-muted blur where data should have lived. But in the radio and microwave bands, 3I Atlas was wide open. It was as if the object was intentionally blocking human visible frequencies while allowing long-wave instruments to continue observing or receiving. Some speculated that the veil wasn't meant to hide anything at all, but rather to tune Earth's observation attempts, redirecting our focus to longer wavelengths, where different kinds of patterns might emerge. Others weren't so optimistic. To them, this was a form of shielding, like a smart window that turns opaque to prying eyes. A technology designed to minimize detection, or perhaps to protect something inside from being scanned. Either way, the veil indicated a level of control. It wasn't chaos, it was curation. The idea of selective observability took hold, an object that doesn't just reflect or emit light passively, but chooses what information leaves its surface. As one physicist from Caltech said during a closed seminar, this isn't a comet, it's a controlled interface. If 3I Atlas was wearing a veil, it wasn't because it was hiding in fear, it was because it was watching back and deciding, minute by minute, what we were allowed to see and what we weren't ready to handle. As the anti-reflection veil confounded Earth-based observers, another revelation unfolded, not in isolation, but in relation to a separate distant object, the Swan anomaly. Previously thought to be unrelated, this diffuse, unusually bright object picked up by the Solar Wind Anisotropes, SWAN instrument, aboard the SOHO satellite, had been quietly trailing its own path through the outer solar system. It was faint, ambiguous, and initially dismissed as a rogue hydrogen cloud. But everything changed the moment 3I Atlas passed its orbital plane. Data from early December showed something shocking. The two objects, 3I Atlas and the Swan anomaly, had begun moving in harmony, not gravitationally linked, not in tandem like binary stars, but their angular velocities and trajectory shifts began matching in eerie parallel. It was as if 3I Atlas was using the Swan object as a distant beacon, or vice versa. This wasn't a simple co-trajectory. Instruments began picking up synchronized emissions, most notably in the Lyman alpha spectrum. As 3I Atlas altered its spin and began displaying a new alignment of its tail and jets, the Swan object flared, 5 hours later. Then, when Swan shifted its signature on December 7th, 3I Atlas responded precisely 33 hours after. The timing was too exact, too consistent. Scientists dubbed the phenomenon temporal eco-alignment. The pattern suggested communication, not in the traditional sense of radio signals or digital pulses, but in synchronized changes across space. This behavior was not only outside the realm of natural cometry dynamics, it was outside the realm of coincidence. SWAN, for all its mystery, had no visible nucleus. Its emissions were gaseous, but without any heat source that could explain their strength. And yet, when 3I Atlas pulsed, SWAN dimmed. When SWAN surged, 3I Atlas adjusted trajectory. Like a mirrored dance across millions of kilometers, theorists were divided. Some proposed a shared origin, perhaps ejected together from an interstellar source, two components of a fractured larger entity. Others saw something more advanced, inter-object signaling, one acting as a decoy, the other as the carrier. Or perhaps both were transmitters, exchanging invisible information through synchronized chemical or magnetic fluctuations. A daring paper submitted to Archiv hypothesized that the two objects formed a quantum-linked observational relay, one designed to mask or delay observational truth through echo latency. This theory, while speculative, attempted to explain the uncanny symmetry in their behavior. If 3I Atlas was hiding behind a veil, maybe SWAN was the lens. NASA and ESA remained silent, but internal memos leaked through academic circles revealed growing unease. Multiple satellites attempted to triangulate the SWAN anomaly's origin, only to find the object's position kept shifting slightly, never randomly but in rhythmic arcs. A sequence of notes from the Parkes Radio Telescope in Australia mentioned a chilling observation. SWAN's brightest emissions always pointed away from Earth. It wasn't showing itself to us. It was signalling elsewhere. By mid-December, both 3I Atlas and the SWAN object began shifting toward new orbital vectors that, if projected, would intersect Earth's orbital plane within days of one another. Though separated by millions of kilometers, the timing was too tight to be chance, and if SWAN was a decoy, Earth was now directly in line to see whatever it had been distracting us from. The synchronization wasn't just spatial, it was behavioral. 3I Atlas was no longer the center of the mystery. It was now part of a system Earth had unwittingly stepped into. In the moments following the observed synchronization between 3I Atlas and the SWAN object, telescopes across the globe locked in on a subtler but even more alarming development. A series of rhythmic emissions, barely detectable at first, began repeating between the two celestial bodies. These were not random bursts. They followed a precise interval, 6 pulses from 3I Atlas, followed by 6 pulses from the SWAN anomaly, each separated by exactly 11 minutes and 2.7 seconds. This became known as the twin pulse loop. To the unaided eye, nothing changed. But to sensors tuned into ultraviolet and soft X-ray wavelengths, something extraordinary was unfolding. These pulses were not only identical in structure and timing, they were coherent, meaning the waveform shape, intensity decay, and signal duration were exact mirror reflections. Despite the distance, despite the supposed randomness of natural cosmic activity, 3I Atlas and the SWAN anomaly were behaving like components of a synchronized broadcast system. The phenomenon quickly caught the attention of independent observatories, including radio astronomers in South Africa and Japan. At first, theories proposed basic plasma resonance bouncing between solar wind pockets, but further analysis killed that idea. The pulses weren't shaped like normal resonance echoes. They carried angular modulation, a signature typically associated with information encoding. In other words, something was being transmitted. It's not unusual for comets to emit pulses, especially as they spin and eject material in the direction of sunlight. But those emissions tend to be chaotic, bursts of gas, heat, and ionized material that vary wildly depending on the surrounding conditions. What was observed here was different. These pulses were clocked, with a rhythm so exact it resembled machine logic. The twin nature of the pulses added another layer of complexity. Whenever 3I Atlas completed its cycle of 6 pulses, the SWAN object responded with a perfect echo, but reversed in polarity. It was like a cosmic binary language, oscillating between two unknown entities in a conversation Earth wasn't meant to hear. Several universities attempted to decode the pulses using mathematical models, including binary translations and Fourier analysis. Some claimed to see repetition. Others dismissed it as signal noise. But one pattern kept surfacing. Every third cycle, the pulse amplitude subtly increased, then decreased again, then rose. It resembled a heartbeat, a living loop pulsing across space. NASA's silence during this time grew suspicious. Previously active in issuing cometary updates, their feeds slowed to a crawl. Instruments like the Parker Solar Probe and Solar Dynamics Observatory continued collecting data, but little was shared publicly. However, a few whistleblower posts on internal forums hinted at something deeper. One described the loop as the closest thing to structured intent we've ever seen from a comet. The behaviour sparked intense philosophical debate. Was this natural resonance between two cosmic objects born of the same trajectory? Or was this the artifact of something engineered? A design so foreign we lack the language to interpret it. The idea that two celestial bodies, moving independently through the solar system, could not only synchronize but emit mirrored pulses, shattered expectations about what was possible in cosmic dynamics. More alarming was the trajectory of the pulse vectors. With each cycle, the axis of the pulses began tilting, like rotating beacons slowly aligning. The latest readings showed their convergence pointing toward Earth. If these pulses were messages, Earth was now becoming their common focal point. And if it wasn't a message, if this was energy or instrumentation, we were being targeted by a system we barely understood. The twin pulse loop continued uninterrupted. No flares, no breaks, just the same chilling, mechanical regularity, like a metronome ticking down to an unknown event. Whatever 3i Atlas and the Swan object had started, they were doing it together, and Earth was no longer a bystander. As the twin pulse loop continued its unbroken rhythm, Earth's scientific community began noticing something unusual, not in deep space, but in the upper reaches of our own planet's atmosphere. Specifically, Earth's magnetosphere, the protective magnetic bubble that shields us from solar radiation, was starting to behave in ways that no existing model could predict. Normally, Earth's magnetosphere flexes and breathes in response to solar winds. During strong solar storms, it compresses on the day side and stretches like a tail on the night side. But this time, the distortions weren't tied to any solar event. There had been no recent coronal mass ejection from the Sun, no solar flare, no high-speed solar wind. Yet Earth's magnetosphere was moving, almost twitching, as if reacting to a signal that didn't originate from our star at all. Satellites like the Magnetospheric Multiscale Mission, MMS, and the GOES constellation started to pick up small yet consistent anomalies in the magnetotail region. It wasn't just flux, there were wave packets, rippling through the field with a periodicity that matched the pulse interval from the 3i Atlas Swan loop, and with each loop cycle, those ripples were getting stronger. These were not catastrophic changes, but they were precise, almost surgical. Every 11 minutes and 2.7 seconds, a small distortion would ripple through the magnetic field, not enough to cause damage, but enough to show that something was injecting energy into Earth's natural defenses. The resemblance to electromagnetic testing was uncanny. One veteran field scientist described it as like someone was gently knocking on the door of our shield, over and over, with increasing confidence. The data became impossible to ignore. Auroral monitors in both hemispheres, normally used to track the northern and southern lights, began reporting strange low-level activations at mid-latitudes in areas that should have remained completely quiet. Normally auroras only appear near the poles due to geomagnetic field strength, but in this case, faint glowing bands, thin as spiderwebs, began forming in the skies above Montana, Kazakhstan, and southern Australia. They weren't vibrant like typical auroras. These glows had a pale, shimmering blue quality, silent, eerie, and faint enough to miss without the right instruments. Yet they always appeared in sync with the pulse loop. It became clear that Earth's magnetosphere was now entrained to this external signal. And the implications were staggering. Some theorists posited that the interaction was unintentional, that Earth's magnetic field was simply resonating, like a tuning fork to the energy pulses from these two strange objects. But others weren't so sure. They pointed to the increasing angular convergence of the pulse vectors, now aimed more precisely toward our planet than ever before. The argument was simple. If it's just natural coincidence, why is the field response amplifying over time? At the European Space Agency's Space Weather Division, internal simulations painted an even more bizarre picture. By feeding in the current rate of pulse convergence and magnetosphere excitation, they discovered a critical threshold. If the signal strength continued to rise for another 7 cycles, Earth's magnetospheric buffer might enter a resonant cascade, a runaway feedback loop where minor oscillations become amplified. What would happen then? No one knew. Some models suggested a sudden geomagnetic storm, one powerful enough to knock out satellites. Others feared something far worse, the creation of magnetic null zones, temporary weaknesses in Earth's protective shell, where solar or cosmic radiation could pour through unfiltered. NASA and ESA maintained public silence, but inside closed networks a single word began to circulate: calibration. Because that's what this looked like. Not an attack, not a random alignment, but a test, a slow, methodical calibration of Earth's magnetic shield by something beyond our understanding. And if they were calibrating it, what would come next? As more data flowed in from ground-based magnetometers and low Earth orbit satellites, one observation began to dominate every closed-door discussion. A subtle, oscillating inversion was forming deep within the magnetosphere. It wasn't just ripple effects anymore. For the first time, instruments were detecting a reversal pattern in localized magnetic lines, short-lived, precise, and repeating. In the natural world, magnetic field reversals are not uncommon. Earth itself has undergone complete pole reversals several hundred times over its geological history. But those shifts take thousands of years. What made this event extraordinary was that these micro-reversals were occurring on a timescale of minutes, and they were happening with surgical precision. The reversals weren't global, they were localized to bands of about 120 kilometers across, sweeping longitudinally across the ionosphere. Satellite arrays like the Swarm constellation picked up clear vector inversions in the BEX and bimagnetic components, signatures that would normally indicate a geomagnetic anomaly, possibly triggered by subsurface magma flows or major solar disturbances. But this anomaly was different. It was moving in step with the twin pulse loop that had become the backbone of every observation surrounding 3I Atlas and the SWAN object. Every 11 minutes and 2.7 seconds, the reversal would occur, momentary, clean, and then gone. Then, almost like a pendulum, the field would restore itself before swinging back again on the next loop. It looked engineered. More alarming still was the geographic path of these reversals. Instead of random placement, they began mapping into a recognizable structure, a grid-like sweep across Earth's magnetic equator. If plotted over time, the reversals formed a pattern that slowly curved and tilted, almost like a scanning beam. By now, data analysts across Japan's JAXA, NASA's Goddard Space Flight Center, and France's CNES agency were looking at the same picture. The pulse loop wasn't just emitting energy toward Earth, it was reading something. And Earth's magnetosphere, with its highly conductive plasma sheets and responsive inner core dynamics, appeared to be the medium through which that signal was being received, inverted, then echoed back. In many ways, it resembled what SETI scientists called a coherent backscatter pattern, an effect observed when electromagnetic signals interact with structured fields. It's often used in radar experiments to determine the properties of distant objects. But in this case, Earth was the object. Some theorists began calling it the planetary ping, a term describing this repetitive rhythmic probing of Earth's shield as though it were being sonar mapped with magnetic resonance. Others took it further. Was this a field integrity test? A way to analyze Earth's core composition by seeing how the field bounced and reversed? If so, the implications were unnerving, because just like sonar is used to map the ocean floor, this magnetic scanning could, at least in theory, be used to reveal or target structures buried deep within Earth's crust. From nuclear silos to mineral concentrations, and from magnetic anomalies to planetary vulnerabilities. The reversal signatures may not be passive at all. And then came the second shock. On December 19th at 03:11 UTC, the first bifurcation event was recorded. Instead of one reversal band, 2 occurred simultaneously, but at antipodal points on the planet, one in the southern Atlantic, one in northern Mongolia. The event was perfectly synchronized but mirrored. For just 2.3 seconds, Earth's field dipped into a harmonic twin pattern, where each point echoed the other across the core. And then, silence. Within hours, the term field reversal signature became the new classification in restricted access defense channels. The Pentagon, NORAD, and European defense ministries were all briefed under electromagnetic threat scenarios. No one claimed to understand it fully, But everyone agreed. Something was now interacting with both sides of the planet, as if Earth was being triangulated, measured, compared, probed, and possibly aligned. While most eyes remained fixed on 3i Atlas as it passed through the magnetotail's grip, a quiet alert began circulating through international observatories. The Swan object was off course. Subtle, almost unnoticeable at first, the deviation showed up in deep space tracking algorithms used by the European Space Agency's Gaia Observatory and NASA's DSN antennas in Canberra. What was once a smooth, predictable trajectory had now become something else, something chaotic, yet eerily purposeful. The detour didn't follow Newtonian drift or cometary turbulence. Instead, the Swan object performed what could only be described as a controlled vector adjustment, a maneuver that resulted in a trajectory spiral tightening its orbit slightly around the Sun while shifting inclination by several degrees. This wasn't just strange, it was unprecedented. Most interstellar objects entering our system follow hyperbolic escape paths, pulled by the Sun's gravity, flung around then sent out. They don't course correct, they don't perform retrograde shifts, and they certainly don't emit polarized plasma bursts in reaction to localized events, which is exactly what Swan began doing within 14 hours of the 3i Atlas reversal patterns. In the early morning hours of December 20th, both the Solar and Heliospheric Observatory, SOHO, and the Bepi-Colombo Magnetometer Array observed something disturbing. The Swan object's wake began generating toroidal plasma spirals, each of them synchronized with the twin pulse loop originating from Atlas. The twin resonance wasn't just symbolic, it was real. The two objects were now operating in tandem, mirroring magnetic activity and adjusting their relative distances. Then came the most shocking shift. Instead of following its previously predicted solar bypass, the Swan object shifted its perihelion, its closest point to the Sun, to align more directly with Earth's orbital plane. This single maneuver reduced its estimated pass-by distance by more than 14 million kilometers. The revised course now placed Swan's closest approach within just 9 lunar distances, an uncomfortable proximity, especially for an object that still lacked full spectral classification. Telescopic visual data didn't help. The object still refused to resolve cleanly. High magnification captures from Chile's Gemini South showed a shell-like glow, layered and asymmetric. Unlike traditional cometary halos that stream evenly, this one shimmered with multi-phase ionization, as if it were coated in materials reacting differently to solar wind. Even stranger, a faint bluish line, barely detectable, was spotted connecting it to a distant dot, 3i Atlas. At first it was dismissed as image noise, a lens artifact, but as more observatories reported the same line at the same angle, it was added to the anomaly list under the term coherent ion bridge. Think of it like a fiber optic cable of space dust, visible only when illuminated by cosmic rays at the right angle. Scientists began speculating that this wasn't a detour at all, it was a rendezvous, that both objects, despite being separated by tens of millions of kilometers, were now part of a shared protocol. Whether gravitational, electromagnetic, or something unknown, Swan's shift placed it in perfect alignment to receive, amplify, or even relay signals or energy from Atlas. The implications were chilling. If this was part of a system, 2 nodes instead of 1, then the interstellar arrival of 3i Atlas wasn't random. And Swan? It may not be a separate object at all. It might be a mirror unit, a listening post, a power source, a behavioral partner. And Earth? Increasingly, it felt like we were inside their line of sight, perhaps even their target zone. What began as a passive encounter now looked like orchestration. The question was no longer, what are these objects doing? But, why are they synchronizing near us? And more urgently, what happens when they finish syncing? As the Swan object rerouted with eerie precision, Earth's magnetic environment began to register something equally disturbing. Pulsing echoes rippling through the planet's magnetotail, spaced at almost perfect intervals. To the untrained eye, this would seem like background noise, normal space weather fluctuations triggered by solar wind or geomagnetic activity. But seasoned heliophysicists saw the difference immediately. These waves weren't chaotic, they were structured. They weren't random, they were repeating. At precisely every 42 minutes and 12 seconds, a new wavefront rippled through the extended magnetotail, starting far beyond the Moon's orbit and folding back toward the planet. The signal's frequency didn't match any known solar cycle. It wasn't tied to flare bursts or coronal mass ejections. It wasn't even a harmonic of Earth's Schumann resonance. The echo had its own rhythm, isolated, intelligent, and disturbingly predictable. The first to detect it was the Cluster 2 mission, a European Space Agency array of 4 spacecraft designed to measure magnetic interactions between Earth and the solar wind. Cluster's instruments lit up with irregular magnetic disturbances just outside Earth's night-side boundary. The strange thing was how coherent the pulses were. All 4 spacecraft recorded the same waveform, the same amplitude drop, and the same rebound phase. That never happens in open space. Shortly after, NASA's Themis probes, stationed in Earth orbit to study auroral substorms, picked up the same data, this time closer in, almost within the magnetosheath. Their readings confirmed the worst fears of the monitoring teams. The waves weren't dying out as they moved inward. They were growing stronger. By the time the echo reached Earth's inner magnetosphere, ground-based magnetometers in Alaska and Finland were flashing warning codes. Radio observatories began to pick up sideband interferences, low-frequency disturbances that warped the local ionosphere and bent long-range radio signals in strange directions. And through it all, one pattern repeated. Each echo seemed to respond to solar wind pressure, but in reverse. When solar wind weakened, the echoes intensified. When solar wind strengthened, the echoes dimmed. This anti-correlated behavior sent theoretical physicists scrambling. It hinted that the source of the waves wasn't solar. It was extrinsic, something behind Earth, something reacting not just to space weather, but to us. Then came the shock. On December 21st at 02p08 UTC, a new form of the wave appeared, one that wasn't magnetic but electrostatic. Detected by the Japanese ERG satellite, this new pulse began carrying banded frequency layers, almost like audio fingerprints. The waveform wasn't just a pulse anymore, it was beginning to look like data. Encrypted, compressed, and utterly foreign. Within hours, the wave was dubbed the Tail Song by amateur radio astronomers, many of whom recorded the pulses with homemade VLF antennas and shared the signal online. Spectrograms of the echo revealed harmonic overtones that resembled chord intervals. Not natural noise, but something with deliberate spacing. What was this sound? Who, or what, was sending it? The working theory from the MIT Haystack Observatory was stunning. The pulses were magnetotail reflections of earlier interactions between Earth, 3I, Atlas, and the Swan object. In essence, they were delayed reactions, echoes of a space-based dialogue that had occurred hours or days earlier, now reverberating through our planetary shield like the replay of a deep space drumbeat. It was as if the Earth itself had become a resonating chamber, its magnetotail now acting like the vibrating string of a giant cosmic instrument. The timing, the symmetry, the source location, it all pointed to something more than natural interactions. This was a deliberate act. But was it communication? A warning? Or was this the byproduct of something even larger? Something using our planet's magnetic field as an amplifier? As more echoes poured in, and the rhythm held steady, one question grew louder in the minds of scientists worldwide. Is Earth part of the message, or the recipient? While the global scientific community tried to decipher the rhythmic pulses streaming through Earth's magnetotail, another stranger void began to form just behind the planet, an area of absolute silence. It came to be known as the Silent Cone. In the vast invisible architecture of Earth's magnetosphere, most satellite sensors constantly register a storm of charged particles, wave turbulence, and electromagnetic interactions. These readings help space weather experts understand solar activity, shield astronauts, and maintain satellite integrity. But in one small sector, centered along the magnetotail's axis, approximately 1 million kilometers behind Earth, everything abruptly went dark. Satellites that passed through this zone didn't detect low-frequency echoes. They didn't detect static or noise. They didn't detect anything at all. It was as if some cosmic mute button had been pressed. At first, it was dismissed as an instrumentation error. The Artemis probe, designed to study the farthest reaches of the Moon's plasma wake, was the first to pass through this region. For 32 minutes, all magnetometer, plasma, and radio sensors recorded an eerie flatline. Then, As the probe exited the zone, full telemetry resumed, intact, undamaged, and baffling. Next came confirmation from the Solar Terrestrial Relations Observatory, STEREO. One of its twin spacecraft in solar orbit but aligned with Earth's tail passed just near the boundary of the silent cone and recorded the same strange phenomenon: complete data nullification across a very specific vector. Unlike previous anomalies, this wasn't an interference pattern or an overloaded sensor. This was pure selective silence. Not an absence of signal, but a deliberate removal. Scientists began referring to the phenomenon as a magnetotail shadow node, a term usually reserved for theoretical models of cloaking, in which certain frequencies of radiation are bent or redirected around an object. Except this time, the object wasn't visible, and the cone wasn't casting a shadow. It was absorbing awareness. To make matters stranger, objects that passed through the silent cone briefly lost orientation. Artemis experienced a sudden pitch shift. One of the CubeSat relays ejected by NASA's HARP project spun unexpectedly, as though it had passed through a zone of altered inertia. But telemetry logs showed no gravitational anomaly, no pressure shift, and no electromagnetic drag. This wasn't a force. It was an absence of force. It became clear that this void was not simply an empty space. It was a space where the laws of detection broke down. Something in this region was capable of absorbing not just light, not just magnetism, but observation itself. The implications were enormous. Was this cone a cloaking field, a communication blind spot, or a staging zone for something yet to come? Some theorists believed that 3I Atlas, or the SWAN object, had left behind a sensor null structure, perhaps to conceal part of their operation. Others speculated that the silent cone was an anchor point, a stable pocket in space from which real-time telemetry was impossible, but where massive calculations or signal redirections could occur. But one hypothesis shook the teams at NASA and the European Space Agency more than any other: that the silent cone was not natural, not instrumental, and not passive. It was a sentient blindfold. Something was watching us, understanding how we observed the universe, and then deliberately removing itself from our frame. An entity with the ability to control when, where, and how it could be perceived. And the moment it stepped into the silent cone, it became undetectable. No heat, no particles, no light, no waves, no trace. In a universe governed by light-speed communication and magnetic fields, the silent cone was a new kind of silence, one that could mask the presence of entire objects, fleets, or even intentions. If this was a shield, what was behind it? And if it was a window, what was looking through it? It began as a small spike on a ground-based neutrino array in Antarctica. For just under 8 seconds, the IceCube Neutrino Observatory picked up an anomalous burst, unusual not because of its strength, but because of its trajectory. Instead of arriving from deep space or following the high-energy patterns of known astrophysical sources, the burst came from within the Earth-Moon system. Even stranger, its origin vector clashed with the known orientation of the 3I Atlas tail, which had recently flared due to solar excitation. The trajectory made no sense. It pointed directly away from Earth's magnetotail, at a sharp diagonal angle. Scientists called it a misaligned burst, and that misalignment was more than inconvenient. It was impossible by standard physics. Typically, neutrino emissions align with the motion or decay of their sources. For instance, when a comet ejects material under solar pressure, the outflow aligns with its orbit and solar wind patterns. But this burst? It was off-axis, as though something had fired it intentionally, away from 3I Atlas's path, away from the sun's pressure, and even away from Earth. Initial suspicion fell on cosmic rays, but as more data poured in, 3 other observatories across the globe, Super Kamiokande in Japan, Antareas in the Mediterranean, and Baikal GVD in Russia, all confirmed the signal. Same burst, same signature, same impossible angle. All 4 detectors clocked the burst within the same 9-second window. Its energy? Roughly 15 tera-electron volts, far lower than gamma-ray bursts, but far more than standard solar emissions. That placed it in a strange in-between category. Too weak to be astrophysical, but too deliberate to be natural. Most disturbing was the shape of the signal. It was not chaotic or decaying. It had a rhythmic modulation, as if someone, or something, was controlling the pulse width. When IceCube filtered the data, the waveform revealed a tritone echo. 3 peaks, each with decreasing amplitude, followed by a flat line and then a mirrored return. The sequence high, mid, low, silence, low, mid, high. It was mathematically symmetrical, eerily so, like a ping test across an invisible axis. No known comet, satellite, or debris fragment had ever produced such a signature. And then came the triangulation. NASA and ESA teams ran simulations on the burst angle and timestamp. When the data was extrapolated backwards through the solar wind and Earth's field, the likely origin point traced to an edge vector just outside the silent cone, the very region where detection had previously failed. In other words, something just outside the undetectable zone broadcasted a burst, but angled it away from Earth, almost as if it was trying to bounce it off something else, or distract. And the target of that burst? It wasn't Earth, it wasn't the Moon, it wasn't Mars or the Sun. It was a point far beyond the ecliptic plane, a point with no known object, a patch of dark space catalogued in star charts as empty, until now. Because 12 hours later, a new object began moving in that void. It wasn't large, barely the size of a small asteroid, but it glowed in infrared, with a temperature profile inconsistent with solar heating. It had received the burst, it had changed velocity, and it was now slowly turning toward the solar system. To many, this was no longer comet science. This was rendezvous behavior. What made the misaligned burst terrifying wasn't the burst itself. It was that it had a target, and that target had reacted. The burst wasn't misaligned. It was aimed, and someone, on our side of the cone or beyond, had sent the signal. Not to Earth, not to warn us, but to wake something up. While most eyes were still locked on the misaligned burst and its ripple effects through deep space, a quieter team within the European Space Agency, ESA, had begun piecing together a discovery that was, in some ways, even more unsettling. Using a sequence of infrared snapshots taken across a 96-hour window, the analysts detected something that didn't match any known orbital model, a precise elliptical loop forming around the comet's trajectory, but not centered on 3I Atlas itself. This loop wasn't natural. It had an entry point, a mid-course vector adjustment, and an exit glide. All signatures that mimicked powered orbital control. And more critically, the entire pattern was offset by just a few degrees from the comet's mass center, as though it were meant to observe 3I Atlas without colliding or interfering with its path. The ESA team dubbed it the Phantom Orbit. To visualize this, imagine a surveillance drone not flying directly above a moving vehicle, but instead circling it at a slanted altitude, always out of the driver's view, but never more than a few hundred feet away. That's what this orbital loop resembled, a co-orbital tail shadow, deliberately carved out to track the comet while maintaining angular separation. What baffled mission control was how precisely timed the loop was. If it were a piece of ice or debris, it would be at the mercy of solar winds, radiation pressure, and tidal forces from both the Sun and Jupiter. It should spiral chaotically or degrade with time. But this object, whatever it was, executed the loop with gravitational indifference, as if it had onboard course correction or inertial dampening. When engineers ran gravitational models through the ESA's Celestia predictive engine, they found that the loop had been timed with 3 Jupiter flybys over the past 19 days. Each flyby coincided with a subtle shift in the phantom object's loop curvature, tightening the pattern like a noose as 3I Atlas neared Earth. What did this mean? Some feared that 3I Atlas wasn't alone, and never had been. The comet might simply be the bright decoy, drawing attention and telemetry while a stealth object performed the real mission, monitoring planetary responses, measuring signal reactions, and perhaps even mapping defense readiness. Others suggested that the orbital loop wasn't just passive, it could be data harvesting. A co-moving object on such a loop could absorb magnetic field distortions, pulse echoes from planetary surfaces, and interference patterns from Earth's radio and radar pings. In other words, it could listen to us without needing to transmit anything itself. The more radical interpretation came from an unredacted section of a report leaked by a Swedish astrophysicist. The document proposed that the object in orbit was not merely tracking 3I Atlas, but might have created it. According to this theory, the comet itself could have been ejected intentionally to test planetary defenses or resource-gathering behaviors across inner solar system bodies. The Loop object, functioning as an autonomous scout, might be assessing the comet's effectiveness, guiding its tail flares, and evaluating electromagnetic reactions. In this framework, 3i Atlas isn't the main actor, it's the bait, and the Loop, that's the handler. Regardless of interpretation, ESA confirmed that the orbital loop had tightened by December 22nd. The distance between the object and the comet was now just 90 kilometers and decreasing. An object maintaining that narrower loop against gravity, solar pressure, and comet outgassing should not exist without control systems. And if it does have those systems, someone designed them, and they're watching Earth from the shadows of a comet. It began as a faint shimmer, one so subtle that most instruments missed it entirely. But the James Webb Space Telescope, with its unmatched sensitivity to infrared fluctuations, logged the anomaly at 0308 UTC on December 23rd. A thermal pulse, perfectly symmetrical, expanding outward from the centre of 3i Atlas like a ripple in a black pond. Except this ripple wasn't in space. It was in infrared wavelengths, propagating at a constant speed in all directions. Not chaotic, not organic, not even gravitational. It was something else, something that behaved like a message. Webb's operators initially assumed it was a reflection flare, possibly triggered by an internal fragmentation, but the telemetry told a different story. The pulse had uniform energy dispersion, and the signature matched none of the heat patterns previously observed from the comet's outbursts or cryovolcanic activity. The frequency, just under 8 terahertz, was also precise. Too precise. That's when a cross-comparison began between other observatories. Within 12 minutes, radio observatories in Chile, New Zealand, and South Africa independently picked up a mirrored signal, not in infrared, but in low-frequency radio bands, arriving exactly 4.2 minutes after the thermal pulse. This timing wasn't random. It matched the delay you'd expect if the pulse had been intentionally bounced off the Moon, or even Earth's atmosphere before returning. The pulse wasn't just emitted, it was part of a loop. More striking than the signal itself was what happened immediately after. Earth's upper magnetosphere began exhibiting coherent resonance lines, waves that matched the frequency of the incoming signal. This meant the pulse had interacted with our planet's own magnetic envelope, not by accident, not by brute force, but through precise harmonic tuning, as if 3i Atlas had sent a frequency designed to interlock with Earth's shielding layer. It was like listening to a symphony and realizing a single violin string had been plucked, in tune, from 100 million kilometers away. Panic was not the official response, but behind closed doors, NASA, ESA, and JAXA held emergency midnight briefings. The nature of the pulse, its precision, its measured delay, its harmonic match to Earth, raised questions that had no easy answers. Was this an accidental byproduct of the comet's activity, or was it the first deliberate signal directed toward Earth? Avi Loeb, always controversial, published a paper within 48 hours proposing that this was not just a communication attempt, but a compatibility test. In his view, the pulse may have been designed to determine how Earth reacts to external stimuli, especially those modulated to interface with atmospheric and magnetic layers. In other words, someone, or something, was trying to understand how to talk to Earth, and this was their first hello. The public would not hear about the pulse for several more days. The story was embargoed, journalists silenced, and institutions issued dry technical summaries of solar interaction events. But behind the scenes, algorithms were already scanning for secondary pulses, and amateur astronomers were now more important than ever. And then, without warning, the pulse reversed. At 0644 UTC, ground-based telescopes captured an implosion wave, returning toward the comet in the same frequency range, but with an inverted waveform. That meant Earth, or something near Earth, had responded. To what? No one knew. But the pulse was sent back, and for the first time in recorded history, humanity had unknowingly participated in a bidirectional communication. Not in language, not in code, but in frequency alignment. A silent handshake across millions of kilometers, a locked gaze between intelligence and curiosity. 3i Atlas had changed everything, and the real conversation had only just begun. So, what do we do now? A comet, once thought to be just another frozen relic from the outer reaches of space, has passed us. But instead of fading into the cold distance, it left behind something we weren't prepared for. It left behind questions. For years, astronomers have tracked thousands of near-Earth objects, mapping trajectories, modelling solar interactions, and cataloguing every flare, tail, and jet. But 3i Atlas didn't behave like the others. It didn't drift aimlessly through space. It aligned, it synchronized, it responded. And when it passed Earth, it didn't just leave a trail of debris or a dusty signature in the sky. It left a message in frequencies, one that touched our ionosphere, danced with our magnetosphere, and whispered something we couldn't translate, but felt. Across every observatory, across every continent, scientists now face a shared reality. We may not be the only ones initiating contact anymore, not with antennas, not with gold-plated records, but with field resonance, spectral modulation, and structured emissions that suggest intention, not randomness. The timeline has shifted. We used to believe we were watching a show from afar, safe behind the glass of Earth's atmosphere. But maybe that glass is thinner than we thought. Maybe what we've been watching has been watching us back. This isn't about panic, it's about readiness. Because if this was a test, if 3i Atlas was scanning Earth's response to harmonic interaction, then the result has already been logged. The response has already been sent. And whatever sent the pulse now knows that we heard it, knows that we felt it, knows that Earth is listening. Where do we go from here? We don't know. But the night skies just got louder. The silence of space feels heavier, and with every passing hour, new signals, new patterns, and new data emerge from the pulse trail left behind. So we'll keep watching, we'll keep listening, and we'll keep asking the questions that scare us the most. What was 3i Atlas? What does it want? And most importantly, was this comet truly passing by, or was this its destination? Thank you for watching. Like, subscribe, and let me know in the comments. What do you think 3i Atlas really is? And as always, stay curious and stay tuned. We're just getting started.